Have you ever wondered what makes music, well, music? Why do some notes just sound so perfect together? As it turns out, the answer is math. Today, we're going to pull back the curtain and look at the hidden mathematical code behind the music we all listen to every single day.
Okay, so let's jump right in with something we've all seen before, a piano keyboard. We're going to focus on these two specific notes, A4 and A5. Now, if you play them, they sound like the same kind of note, right? Just one's higher and one's lower. Musicians call this an octave. But what's actually physically happening to make them sound so connected?
Here is our very first clue. You see, the pitch of any note is all about its frequency, which we measure in hertz. That's just cycles per second. The note A4 vibrates at a neat 440 hertz. So what about A5? It vibrates at exactly 880 hertz. It's a perfect doubling. That clean, simple 2-to-1 ratio is what our brain hears and says, aha, that's an octave.
And check this out. This visualizes the whole idea perfectly. This graph shows the sound waves. The solid blue line, that's our lower note, A4. The dashed red line is the higher one, A5. You can literally see that in the time it takes A4 to do one full up and down cycle, A5 completes exactly 2. It's that simple, elegant relationship that our ears just love.
Okay, so this brings us to the big question, the real puzzle we need to solve. We know we need to get from 440 Hz all the way up to 880 Hz. And we can see on the keyboard that there are 12 steps, or semitones, to get there. So, how do we slice up that perfect octave so that each of those 12 steps feels like an equal jump in pitch?
Now, your first instinct, and it's a totally logical one, might be to do some simple addition, right? Let's find the total difference in frequency, which is 440 Hz. Then let's just divide that by the 12 steps. That gives us about 36.7 Hz for each step. So we just add that amount for every key we go up. Simple. Unfortunately, it's also completely wrong.
And here's the fascinating reason why. Our ears don't hear pitch like it's a ruler. We don't hear equal additions of frequency as equal jumps in sound. Instead, our brains are wired to hear equal ratios as equal steps. So adding 37 Hz to a low note sounds totally different than adding 37 Hz to a high note. We need a different kind of math entirely. So this is the crucial insight, the real game changer. Each step up that musical ladder isn't adding a fixed number of vibrations. No, it's multiplying the frequency of the note before it by some constant ratio. We're not building with simple building blocks, we're building exponentially.
All right, to make this a little easier on ourselves, let's give this magic number a name. Let's call this constant ratio. The number we have to multiply by to go up just one semitone, we'll just call it R. Our whole mission right now is to figure out the exact value of R.
So think about how this works. We start at our note A4, which is 440 Hz. To get to the very next note, A sharp, we multiply 440 by R. Then to get to the next note, B, we multiply that new number by R again. And we keep doing this 12 times in total until we land on A5, which we know has to be double our original frequency.
And all of that leads us right to this beautiful little equation. It means that R multiplied by itself 12 times has to equal 2. And when you solve for R, you get this, the 12th root of 2. This elegant, simple formula, this is the mathematical backbone of pretty much all Western music. It's the secret sauce for what we call equal temperament.
So what is that number anyway? Well, it comes out to about 1.059463. So what does that mean? It means every single time you move up one key on the piano, you're increasing the frequency by about 5.9%. It's this incredibly precise, consistent multiplication that makes the musical scale sound so smooth and even to our ears.
Now you can probably imagine, a number like 1.059463 is, well, it's a bit of a mouthful, right? It's not exactly easy to work with. So musicians and audio engineers came up with a much more practical tool to talk about these pitch differences. They created a unit called sense.
So why on earth would we use sense? Well, as we just saw, working with those crazy multiplicative ratios is a pain. Musicians wanted something simple, something additive, like a ruler for pitch. And the solution was a clever mathematical trick. Use a logarithmic scale. Because logarithms have this amazing property, they turn multiplication problems into simple addition problems. And the system they came up with is just so clean and elegant. By definition, one semitone, that's our multiplicative step R, is equal to exactly 100 cents.
So now it's easy. To go up 12 semitones, you just add 100 cents 12 times, which gives you 1,200 cents for a perfect octave. It's a beautifully practical system that's built on a really deep mathematical idea.
And ultimately, that's what this all comes back to. The incredible emotional power of music, the structure of harmony, the very idea of an instrument being in tune. It's all resting on this invisible, elegant framework of mathematical ratios. It's this perfect fusion, creative expression and pure logical order, all becoming one.
We just found this profound connection hidden in plain sight, right there on a piano keyboard. And it really makes you wonder, doesn't it? What other hidden math is out there, shaping the world we see and hear every day? The more you look, the more you find that the universe really does seem to be written in the language of mathematics. What are you going to discover next?